Hello, this video is designed to help you go over electric circuits, and I'll be covering the basics of voltage, current, and resistance, as well as circuits. So, you can see here in the notes, a circuit is definitely a complete pathway from the negative to the positive end of a power source. And you need to know these two types of circuits. There is a series circuit and a parallel circuit. Okay. Um, Series circuits only have one pathway. That's where everything's kind of hooked up in a chain. We'll see that really quick. And what may not be too obvious right now is that when that happens, the voltage in each device has to add up to the total voltage. What we could say is that you have to share the voltage. Okay, we might say that the voltage is shared. Okay, but that may you'll see how that plays into the other one. Now the current is for a series circuit, the current is the same because the current is flowing through all of the devices and there's only one pathway. So every device gets the same amount of current, if that makes sense. Okay. Now in a parallel circuit, they kind of reverse. In a parallel circuit, instead of one pathway, you have multiple pathways. Instead of the voltage being shared, now really it's the current being shared. Okay. And what's awesome about parallel circuits is the voltage is going to be the same for each source. And we'll look at how that works here in just a little bit. But yeah, the current in each device has to add up to the total current. So the current is shared. So just to maybe highlight that for you, I've got a picture of both. And we'll just make up some numbers here just to make a quick point. So in this, you can see the series is pretty obvious, and parallel, the way we draw it looks just like that. So there's multiple pathways. We could say for both of these circuits, we could say that we had 8 volts of available voltage and say 2 amps of current. Okay, that's our input, if you will. That's how much is coming in. So in the series circuit, that 2 amps of current will flow through everything. Okay, so if you were to stick an ammeter anywhere in there, like in the device or just after the device to the next one, there'd be 2 amps all the way along. 2 amps, 2 amps, 2 amps. Okay, in terms of reading that. And we'll talk about the multimeters in a second too. For the voltage though, each device will share the voltage. So if you have 8 volts available, 8 volts will not be in each device. You would have 2 volts because there's 4 devices. So each device would only get 2 volts. And you can see if you keep adding devices in series like this, they get less and less energy, less and less volts. And so if they were light bulbs, they'd be dimmer, and you'll see that right away. Now, just to contrast that quick with parallel circuits, down here, if you can see the current comes in, but see that 2 amps of current now has to split. Some of it will go up like this, some will come down. So the current has to kind of break up. So what happens is here, I guess you could see it, each device would only get half of an amp, okay, 0.5 amps. All things created equal here. And then, the output, of course, would still be 2 amps by the end because all of those they all flow together, if that makes sense, towards the end. But so sometimes usually that's not an issue for the most part, as long as there's some current flowing. But what's really nice about parallel circuits is here, every device will get 8 volts, okay? Every single one of them, because they are hooked up in parallel. So, if you have 4 light bulbs and you arrange them in parallel, they'll all be really bright and I guess they'll all be the same brightness. They'd all be the same brightness in the series one too, but they'll just be really dim. Okay. And as some of you may remember, if, for a parallel device or parallel circuits, if, we were to if we were to cut out one of these, okay, so let's say that device failed, well, there's still complete pathways for the other three, and so the other three will stay on, and the device one in this case will shut off. So not the case though with the series circuit. If you remember, yeah, if one of these devices, say device number 2, fails for some reason, you've interrupted the whole flow and then nothing's going to work. Okay, so we'll cover those briefly here as well. Now, if you don't remember the relationship between voltage, current, and resistance, here it is here. George Ohm was the one who explained that relationship. Essentially, he said that as long as the temperature stays the same, then in a circuit, then the resistance in that circuit should stay the same. And the resistance, it can come from resistors. Often it's just the metals that are used in the circuit themselves. Resistance is a measure of how hard it is for the current to flow through the circuit. And as you can see, all of those units are there. We've already talked about voltage and current. Voltage is measured in volts and current is measured in amps, but resistance is measured in ohms. And there's that symbol omega, that's the last letter in the Greek alphabet. We use that to represent ohms. So you'll see that in all of the examples from going forward. But this math isn't horrible. As long as you're comfortable with like a 3-variable relationship here, you can manipulate and solve for whichever one you need. Just make sure you keep track of the units. So you should learn, or you need to know how to measure all 3 of these using a multimeter. So this is a multimeter here. And as you'll see on all of them, there are settings on here for volts, okay? This first one is actually for AC voltage, which we don't really measure too much, but you saw a picture of that in the other video. This one here is DC volts. There's the Greek letter omega. So that's ohms. And then here is amps, which is current. And there is just this little guy right here. I think that's a continuity measure, meaning if you hook that up to your probes, you can tell if there's a complete circuit or not. So anyways, multimeters are super handy. If we're measuring current though, you can see that this dial here, let me clear all this off. You can see that this dial has been rotated to point to amps, and it's specifically pointing to the 200 M for milli, okay? And again, these prefixes are on your data booklet if you ever have to look them up. Because yeah, look, there's mu, there's 10 to the negative 6, and we have K's in here, which is 1,000, and so on and so on. So to measure current though, as it says, we need to basically set the multimeter to current, and then you need to make the probes part of the circuit, okay? So this here is just a power source, and the power in effect, it says you have negative and positive, so the power is coming out of the negative terminal, will go into the multimeter, and then to the positive terminal in that direction. Okay, so here we're measuring the amount of current in amps, and it looks like it's 8.52 milliamps. Now, yes, it's going through a resistor. If you've never seen these before, we'll see one in just a minute. They're made of different metals, and they have little color bands on them to identify how much resistance they have. It's just a format or a convention that they use for resistors. So when you see those, that's what those little bands are for. Anyway, so hopefully that's not too bad. That's how you'd set up for current. The positioning, if you really are looking at using a multimeter, the position of these probes is important. You can see there's, if you are looking to solve, or if you're looking to measure current, you need to put the red one in the top hole. But if you're switching to voltage, you would switch that one down here. The COM here, I think that one just stays there the whole time, if I remember right. It's been a while since I've used some of these multimeters for a whole bunch of different things. But anyway, so that's how to measure current. Let's measure voltage. Voltage is, you switch the multimeter here to volts. So here, this one's set to DC volts. If you can see that, it's like right here, that little white bar there is pointing at the voltage. And you still have the power source hooked up, but here we don't need to make the current flow through the multimeter, because the current is just flowing through the resistor like this. That's where the current's going. What we're doing is we're just bringing in the probes, in this case, to measure the potential difference across the resistor, okay? So we call that, well, I guess in this case it would be parallel. That is a parallel hookup, as the notes mentioned, but we're really measuring the voltage across that part of the circuit, okay? And yeah, actually it does show that we did move that red, we did move the red probe down to that position, if that makes sense. Not that you'd have to really know that, but you may see pictures of a multimeter and you got to say what it's measuring. So in this case, with that dial pointed there, we're definitely measuring volts. And it looks like we have, 4.34 volts, okay? So that's how you measure voltage. The third one is resistance, and this one's kind of similar to voltage. We need to basically place our probes at the beginning and the end, if you will, of the resistor. The only difference here is we're not running current through the resistor. As noted here, number 3, we basically do the same steps, set the multimeter to ohms, place the probes before and after the device, and then, but we don't run current through it, because that would compromise your reading. So, yeah, so that's measuring resistance. And in this case, based on our settings, it's 0.512 ohms, okay? Because we did set it to this 2K reading, 2000, and so it's not even, it's a fraction of that. But anyway, yeah, I put a little picture here. Resistors are everywhere. Oh my goodness. If you ever rip open an electronic device like an old DVD player or an old TV, or even if you're unlucky enough to break open a computer, you'll find these circuit boards, and these look like little cities. They're just fascinating, but there's all kinds of power inputs, and essentially every cylinder that you see here, there's a couple of green ones right there. There's a blue one. There's another one right here. If you see, and really all of these little guys too, all of those are resistors. They are all positioned to control the amount of current that's flowing into this circuit board and is running a whole bunch of devices like little sensors, integrated circuits, microchips, fans, cooling fans, LED lights, you name it. Everything is all there. But the point is that all of the current that's coming in from your, basically that's coming from your wall when you plug it in, you don't want all of that current to go through every single device in, say, your DVD player or your laptop, because that's way too much current or way too high a voltage, and you have to control it. So there's a lot of fascinating technology behind these, and we've gotten so good we can make them for almost nothing in terms of making electronics that are cheap, because we basically have robots and computers that will do this for us. So that's resistance. So that's actually physically measuring it, and we'll do some of that a little bit later. I won't read through these, but I do want you to look over these examples. Anytime you're given a question that gives you, say, like in this one, it tells you the current and then it tells you the voltage. If you need, and then it says determine the resistance. Well, you're just using this equation. Voltage equals current times resistance. You can manipulate it to solve for, in this case, resistance, and then you can find what it is, and it'll always be in ohms. And these questions are also pushing you to note if you're dealing with DC current or AC current. DC current or direct current always comes from batteries. Okay, so your cell phone runs off of DC current. Your laptop does when it's running off of its battery. Batteries provide DC current. AC current comes from alternating current sources, which are the power outlets in your house. Basically, the electrical energy, the electrical power that's coming to your house is alternating current, okay? We have Nikola Tesla to thank for that one. Anyway, but so that way you know, you can just, sometimes we'll ask a question about the source. If you know it's a battery, it's DC. If it's coming from your house or from a power outlet, it is AC, alternating current. So I'll maybe just highlight these quick because you know you don't have the answers here. 32, again, it shows you, and as you read a question like this, I hope you can just catch how the setup isn't too bad. It says a low intensity light bulb is operating. It uses one of the 120 volt household circuits and it draws 0.25 amps. So the first question says, is this current AC or DC? Well, if it's using a household circuit, it's going to be AC. And what's the resistance? Well, resistance is equal to voltage divided by current. Okay, based on that formulas. And again, you'll have those formulas, so don't stress about trying to memorize them, but they're not too bad if you do. Voltage, though, is 120, and the current is 0.25 amps. So dividing that, then we wind up getting 480 ohms. Okay, so we'd write it like that. That'd be the resistance of the bulb. Okay. The next one is very similar. We'll do that one quick too. If you've got 4 cells in a flashlight and they are in series, you would add up all those voltages together. Each typical cell is 1.5 volts. If you're familiar with that, when you purchase cells and batteries, 1.5 is the standard voltage for a cell. But yeah, we got 4 of those. Bang, we just add 1.5 times 4 gives you 6. And it says in this bulb, the resistance is 8 ohms. Now, is the current AC or DC? Hopefully you can see that is going to be DC because we're dealing with a battery, or sorry, yeah, this is a battery, multiple cells, right? So the current then, in this case, the current is equal to the voltage divided by the resistance. So 6 volts divided by 8 ohms, okay? That will give us 0.75. And yes, we just measured current. Sorry about that. We measured current. So the units here are going to be amps. Okay. So again, I don't think that's too bad. I think you guys can handle that, no problem. So the second part of this is understanding drawings of circuits. And so we call these schematics. You might remember that from Science 9. You should know these symbols in general. They're pretty straightforward if you can remember what they do. And if there's any weird ones, you'd get a key or something that would explain them. Okay, so just worth mentioning here, if you remember, like a switch in general, this switch is open, but if we closed it, so we drop that door down and just close the switch, then the circuit will be operational, then current will flow and the light bulbs will go on. You'll see that when I show you an example here. Cells are worth noting. A cell just has a positive and a negative terminal. The negative terminal is always the smaller of the 2 lines, okay? So this side's negative and that side's positive. And yes, if you jam a bunch together, like in the example we just talked about in that flashlight, I put 4 of them together, you still have a collective negative and positive terminal. But yeah, you're just getting, the voltages will add together, and we'll see how that works too. So a resistor is just kind of like some jagged shark teeth or whatever. And then lamp and so on. Okay, so a simple circuit here is showing a source, just a single cell. It looks like we've placed an ammeter in the circuit, see? Because the current is going to go from negative to positive, and the current is going to flow through the ammeter. So the current's going to go like this through the ammeter, it'll read it, and it's going to go through this resistor and then all the way around. Now the voltmeter is not part of the circuit. It's set up in parallel, if you can start to see that configuration. And this voltage would just be reading the voltage across the resistor. Okay, so where we're headed here is calculating the totals for voltage and for resistance. Now, and they're really not that bad. If you have a bunch of cells in series, like we just discussed, the total voltage, that's what VT series, it means the voltage total in series, you just add them up. So this schematic is matching it correctly. Okay, so here's the positive and the negative terminal. So we have the positive and negative terminal, and they're connected to another one and to another one. Okay, and the benefits here, this is important to note. If you do this, you can get more voltage. Like you can grab a bunch of 1.5 volt cells and you can rack it up to like 12 volts or whatever you need in terms of huge amount, like higher amounts of energy per unit of charge. Okay, so and that will also result in an increase in voltage too. But so sometimes that's advantageous. Now, other times you don't want to do that because you can deplete these cells a little bit quicker when you do it that way. And so the other configuration is to put them in parallel. And so here you've got it over here. It shows the cells lined up in parallel. And in this case, the total voltage is equal to the voltage across any one of the cells. Hence this expression here. So the voltage total in a parallel circuit is just equal to the voltage across any individual cell. And I like this schematic as well. It shows accurately the negative and the positive terminals again, but it shows that they're in parallel. Okay, so the negative, all like the negative current flows out of all three of those and goes outwards. Okay, and then it comes back into all three of those above. Okay, so anyway, they're in parallel. Now again, what's the advantage? The cells can last longer because you're not going to deplete just one, or you're not going to deplete three cells at the same rate as you deplete one if all three of them or just the one of them are powering, say, one light bulb. Okay, three cells hooked up in parallel, it'll take a lot longer to drain all three of those than it will just to drain a single cell. Okay, so again, this one's really good. All the electrical power that comes to your house typically comes in through three cables. Okay, three wires. As it says, two of each of these wires have voltages of 120 volts each. And we'll learn that in the next chapter. The voltage has been stepped down to 120 volts in the two hot wires, if you will, right? There's the neutral wire and there's the two hot ones. So those are coming into your house. Now, in fact, all of the standard power outlets in your house are wired to take only 120 volts. So the appliances that demand 120 volts, the circuit that you need, because you remember you have two of these coming in, you're going to need a parallel circuit. Okay, and that's what the answer says here. Okay, so in this case, you have them both coming in, but actually I won't try and draw that. But the solution here is the voltage. You'll need the two wires need to be wired in parallel so that you can only get 120 volts. Now, your dryer and your oven, and if you're lucky in your garage, you might have a small welding tool or maybe an electrical saw. There's some other, or if you're really lucky, you have an electric car that is charging with a 240 volt outlet. How do we get that? Well, you might see it now. All we have to do is take those two incoming wires that come into your house that are wired for 120 volts each, and you wire them in series. So that means that the voltages add together and we can get 240. So the highest voltage you can get in your house anyway is 240, and that's just standard. You can get more than that if you're a restaurant owner and you gotta get some serious voltage coming in for a bunch of devices. You can get some different transformers and get higher than that, but standard home, the maximum voltage you can get is 240. Okay, so let's do this one. So this one focuses on laptop computers, and they use 3.6 volt cells, lithium ion cells. So each one of these little cells is 3.6. Okay, you guys get the idea here. So it's cool though, because they call them a 4S2P configuration. And what that means is that's four cells in series, that's the S, but then two parallel. so that you have two sets of those 4 series cells, 2 sets of them in parallel, 4s2p. That's just kind of cool. Anyway, so if you look at this, the question says, if the 4 cells in each series combination are rated at 3.6 volts, what's the total voltage? Well, you just go 3.6 times 4, right? That just for that top part, that would give us 14.4 volts, okay? And that's obviously what would be the same in here as well, okay? So they both have 14.4 volts. Now, what's the total voltage of the whole pack? Well, they're in parallel, okay? So these 4 series cells are in parallel. So the total voltage is 14.4, okay? So, you put your voltmeter out here and you put it out here, you test it right there and there. The total voltage is 14.4. So anyway, that's a nice combination because we need that much voltage, but we also don't want to drain these cells very fast. We want them to last a long time. So anyway, the combinations are almost infinite here. And I'm not an expert on the technology, but man, companies that are making, like for example, a Tesla car uses over 7,000 cells. It's nuts. And they have them in a very specific series and parallel combination, not 4s2p, but it's similar. And they get the voltages they need and the long-lasting life that they need, because you're trying to make a battery that lasts a long time, but that can also deliver the voltage when you need it. So anyway, very, very fascinating. So this is what we want to end on here, is calculating resistance. So that was just calculating voltage. Let's look at resistance. So what it's showing you here is just showing a simple circuit to start with. This 6 volt, 6 voltage available, 0.6 amps of current, and 1 light bulb. And it's just saying, well, what if we make it a little more complicated, and instead of having 1 light bulb, we have two light bulbs in series, or we can put 2 light bulbs in parallel. And what's interesting is it looks like the current dropped down, okay, in the series circuit. It went from 0.6 to 0.3, but then in the parallel circuit, it went up. Like it went from 0.6 amps all the way to 1.2 amps, like it doubled. So how did that happen? And what's going on here? So before we break this down, I actually want to show you this in a quick animation, because this is the one that you can play with. I put a link to this here. It's just fun. You can mess around and do a bunch of stuff. I took some liberties here, and I put 2 cells together instead of just 1, and I made 3 light bulbs in series and 3 light bulbs in parallel. If I had time, I could show you how the current changes. But anyway, so just to show you here, we turn the current on, and with the switch, right? Open and close the switch, and all 3 of these light bulbs light up. Now that's not too surprising, but let me just show you quick here if we use a voltmeter. So I'll bring the voltmeter in here, and we'll put it at one end of the my 2 cells, and at the other end, and it says got 18 volts. Okay, wow, so it basically looks like we have 2 9-volt cells that are connected in series, or 2 9-volt batteries. So get a total of 18 volts. Now, if I come down and I measure the voltage across each light bulb, okay, whoops, I got to get that one to touch it. It's only 6. See, that one's only 6 volts. And from there to there, it's 12. But if I just go over each individual light bulb, I only get 6 volts. So can you see how that works? The voltage is shared. It's shared over all 3 light bulbs. And so what it means is there's only 6 joules of energy per coulomb of charge. Like these little blue dots going around could represent coulombs of charge. And it's only getting 6 joules of energy per coulomb of charge to each light bulb, okay? Just for reference too, we can actually pull the ammeter in here, okay? So ammeter, we'll just throw it in here. It says it's 0.6 amps. 0.6 amps, 0.6. See, look, the current is the same everywhere, in the light bulbs, all over, okay? So Fairly low current, but hey, there's only one path for it to take, so it's the same everywhere in the whole circuit. Okay. Now there's some other cool things we can talk about that, but let's just jump to the next one. So just for contrast, okay, I have the same cell, so there's still 18 volts. In fact, we could even check that quick. This should be 18 volts. Yeah, it is. Okay, so let's get that out of the way. Let's just light this guy up. Whoa! Okay, so maybe you were expecting that, but look at the light bulbs. They're way brighter, like all three of them. And whoa, we got some weird stuff going on with current now. So what's interesting is the light bulbs actually have some resistance, okay? And we could, actually, I don't have an ohm meter on here, so I can't measure that. But anyway, the light bulbs actually slow down the current. And if you can kind of tell, see the coulombs of charge are going really, really fast at first. And then when they're in the light bulbs, they're going quite slow, and then they speed up again. So that's meant to represent the change in current. But anyway, let's do the voltage first. This one should make a little more sense now. So the voltage again across my cells is 18. Let's see what the voltage is across the light bulb. Okay, so this one, oh, that's 18. Look at that. And look at this. You know what? It doesn't matter where I stick these probes, does it? Because I'm in a nice parallel circuit. Man, everything is 18 volts. So hey, those light bulbs are getting 18 joules per coulomb of charge, and they're way brighter, and they're all the same brightness. So that's awesome. And yeah, just to reinforce that too, if we went up to one of these light bulbs and I removed it, oh, it didn't change anything, right? So for the other two anyway, so they still have the same voltage. Now their current will change a little bit, but the voltage didn't change. So anyway, let's put that light bulb back. Oh dear, no, it's not going to work. So I don't know if I got to get that thing oriented correctly first. There we go. A little cockeyed. That's okay. So yeah, if we were to come over here to one of these light bulbs and remove it, boom, there's no current flow because we've interrupted the circuit. So not you should be too surprised with that. Okay. Now here, let's throw the current in here just for fun, the ammeter. Okay, look at this. I got 5.4 amps right at the source. Okay, do you see that? Now look, you don't have to know the math here, but what's cool is if we get to this branch, look, the current can now split. So it's not going to be 5.4 amps anymore because right at this junction, some of it can go this way and some of it can go that way. And so you don't need to know the math directly for that. But look, there's 1.8 amps in there. There's 1.8 amps there, and there's 1.8 amps there. Okay, so and even inside, so each light actually shares the current, and that's what I meant from the beginning, right? So if I have 5.4 amps available in current, and if it's set up in parallel, then each light bulb will get a third of that. But in terms of the voltage, that's what makes parallel circuits so fun, is the voltage is the same across each circuit. So if you're doomed to have the Christmas lights that are set up in series, then you get over here and yeah, if one of the light bulbs burns out, the whole strand goes out. And you're like, honestly, where is it? Okay, that's really annoying. But most newer Christmas lights are done in some form of parallel circuit, so that if one light bulb goes out, the whole thing doesn't go out, and then you can actually easily find where the one that's burned out is and replace it. But anyway, so I'll let you guys play with that when you get some time, because that is the it helps you understand the basics for circuits. Now, so let's come to resistance. So again, if you have a series circuit, the resistance in each device, you will add those resistances together to get the total resistance. Okay, remember, because the current can only has to go through all the devices. So the total resistance is really easy. You just add them up. Okay. Now if they're in parallel, then what's interesting, if you kind of caught that, is the current doesn't have to go through both light bulbs. It doesn't need to, like it did in the series one. So in parallel, the current comes out here and it can go this way or it can go that way. And so actually what happens is if the resistance, the total, because then the total resistance goes down, that means the current goes up. And that's what happens right there. Okay. So, and yes, it's directly proportional. So if we cut the resistance in half, then the current would double. And that's exactly what happened in this one. Anyway, so what you need to know is the formula is, and this one's in your data booklet. Okay, so if you don't remember it, it'll be there. You have to do reciprocals. So they're a little tricky, but they're not that bad really. 1 over the resistance total will equal 1 over the resistance in the first one plus 1 over the resistance in the second one, and so on, however many you've got. Okay. And when you're done, then you have to reciprocate your answer, because if you just solve for this side, you're just going to get, you'll get a really small number, but that's going to equal 1 over the resistance total. So if some of you have an x to the -1 button on your calculator, you can use that, or you can just say 1 over the resistance total, or 1 over the resistance on the right side. That will reciprocate that, and then you just get RT. Then you're just getting the total. Okay. Some of you, I think, are familiar with that from other math you've had to do. So again, I won't go through all these examples. I'd like you to read them though, because they will help you see how to do this. If you have a whole bunch of light bulbs in series, as this question indicates, to get the total resistance, you just add it up, because in this case, they're all the same resistance. Then you just have to go that amount times 8. Okay. And then, from there you could determine the current, okay, using Ohm's law, okay, which is exactly what this one did. The second one actually deals with connecting lights in parallel. And it's really easy to do on a power strip, as this shows. I think the question deals with 5 lights like this, and if you plug all 5, each one can have its own circuit because of the power strip or the power bar, okay? As a schematic, the drawing would look like this, because you'd have 120 volts as your source, and then each spotlight would have its own circuit, okay? Meaning that if you had to calculate the total resistance, it's going to look like this, which looks a little ugly at first. But I mean, if they're all the same number, then really you're just doing 1 over R total is equal to 5 times 1 over 96 ohms. And you'll see then that the resistance is actually quite low. Okay. It's much lower than the 96 ohms. Okay. And then here's the reciprocation again here at the end. Sorry, that was that little tip there. If you want to use reciprocal, you can use the x to the -1 key. That could then set you up to find the current, because if you found the resistance total, which is 19.2, then you can find the current. Okay. So last thing I'll end on here is often you get circuits that have both series and parallel components. And that's in your house. Okay. So downstairs in your basement, I'm sure you've all been there, if you've maybe seen your parents working on it, is your circuit breaker panel, or the control panel, they sometimes call it. Yes, there's a big main breaker that shows it there in red, but there are a whole bunch of different circuits that are wired in parallel, and each circuit has a breaker. And so if you look at this circuit, on this circuit, there are there's four basically plugins really. And it's just showing you here, they're all kitchen appliances. So on this circuit, if this is the classic one, right? And maybe you've done this in your house. I remember having a home where we had a microwave plugged in, and a toaster and something else. And if we ran all those at the same time, it would trip the breaker. And the reason obviously was because we were drawing too much current. So yeah, if you were running the blender and your toaster and your heating water in the kettle all at the same time, all of those they're all parallel to each other. Like if the toaster, if you unplugged the toaster, or if the toaster like failed, then the blender and the kettle could still work. But what's clever about this design is they all run through a circuit breaker. Okay, so if you're running the pathways, right? So it doesn't say which one's negative or positive, but see, this one would go this way, and if you close the switch, but this one would go this way, and then this one goes this way, and so on and so on. But they all go through that circuit breaker. And as I understand it, the safety rating is about 15 amps. So if more than 15 amps is trying to get through the circuit for whatever reason, then it overheats. This actually generates heat, and it just separates. And you'd hear a click, and downstairs in your control panel, one of these little switches will have flipped over. So it actually will be like sitting over here or something. It'd be like this, okay? Like it would have just like slid over. And you go down there, you're like, oh, well, obviously the power's out. And then you just, you push it to the right and then reset it. And then your power's back on. So anyway, I hope that's helpful in terms of understanding the basics for electrical circuits. I did post the practice questions and the answers. So I'd really like you to take your time and work through those and let me know if you have any questions.